spectrum of activity in your catalyst.
Just a moment, please. I have an announcement. Today's lunch will be served at the room Lily, not Shangri-La. So it's 60 persons. Today's Shangri-La room will be served for lunch buffet style, so we cannot go there. But it's special permission is we can go to Shangri-La room is for another persons, except 60 persons. And then today's menu, as I said yesterday, is a galbi tang, which is a Korean style beef rib soup. Thank you very much.
Thank you.
Thank you very much.
Other people.
It's come back. That's right.
Or just speak up.
Hello.
It's not Professor Cruz.
Turn the mute off.
That helps?
It helps, yeah.
Good afternoon. We're about to start the final session of this symposium. My privilege to introduce the next speaker. The topic will be the effect of fluorine addition on the properties of nickel, tungsten, sulfur, alumina hydrotreating catalysts. Professor Song-Hook Moon received his Bachelor of Science degree in Chemical Engineering from Seoul National University in 1968. He received his Master's of Science and his PhD degree in Chemical Engineering from the University of Illinois in 1974 at the Champaign-Urbana campus. He is presently, he was head of the Reaction Engineering Lab at KIST from 1974 to 1988, and presently is professor in the Department of Chemical Engineering at the Seoul National University since 1988. During all of his studies and his experience, he has spent a few years at Pennsylvania State University, at the University of Delaware, and at Stanford University. Professor Moon.
Thank you.
Thank you for the introduction. Before I start my presentation, let me confess one thing about my English. Being away from the United States, I feel that my English is being deactivated. The reason is not because it's being used too much, just like in the case of catalyst, but it's because it's not being used too much. This afternoon, I think it's going to be worse because of two reasons. When I speak to Japanese or Chinese scholars during the Korea-Japan workshop and Korea-Chinese workshop, my English is a little better because we all speak broken English. So in front of you guys who speak English with native language, I know this is a psychological problem. Another reason, I never spoke in English in my lifetime in front of a movie camera. I was recording every word of my speech, every movement of myself. So this is going to be a very tough challenge for me. Right. Okay, let me start my presentation. Anyone operate the slide, please? The topic that I'm going to talk about is, as introduced, about the effect of fluorine addition and the properties of nickel tungsten sulfide catalyst, which is used in the hydrotreating process mostly for producing lubrication-based stock oils. As you know, cobalt molybdenum or nickel molybdenum or nickel tungsten catalyst, sulfide catalysts are good catalysts for hydrodesulfurization and also for hydrocracking catalyst as a hydrocracking catalyst sometimes. But this nickel tungsten sulfide is particularly good for hydroprocessing for lubrication oil production because it has high activity for hydrogenation only, and hydrogenation also. Can I have the next one, please? It has been known that when we add fluorine to nickel tungsten, the activity of hydrocracking and hydrodesulfurization increases. And we have decided to study why that increases due to this fluorine addition. So we prepared some model nickel tungsten catalysts containing various amounts of fluorine and used thiophenes hydrodesulfurization and also normal heptane conversion in hydrogen to some extent. And also we prepared tungsten and nickel metal alone catalysts for comparison. And we use those catalysts for reactions, and also we try to characterize the properties of these catalysts by TPR and TPS and UV visible diffuse reflectance spectroscopy and in situ FTIR. The experiment, we prepared the catalysts with the identical metal composition. In other words, the nickel content was kept constant 6 weight percent and tungsten 20 weight percent. We only changed the fluorine content from 0 to 4 weight percent. These are the nominal weight percents. We have not checked the actual weight percent. These are the weight percent that we intended to load. Okay, the detailed method of catalyst preparation is as shown here. It has been prepared by a successive incipient impregnation method. First, we impregnated gamma alumina with a solution of ammonium fluoride, and then dried it and calcined it in air for 4 hours, so that we get fluorine added alumina or fluorine treated alumina. We designated it as FX on alumina. X means the amount of fluorine that we intended to put on alumina. And we use this alumina for making nickel, or we loaded tungsten on this support by impregnating this alumina with ammonium metatungstate solution, and then again calcined in air for 4 hours, so that we get this tungsten fluorine on alumina catalyst. And then again we loaded this with nickel nitrate, so that we get nickel tungsten fluorine on alumina catalyst. Okay, we use these catalysts. These are oxide catalysts. So we used these catalysts sometimes for characterization and also for reaction. We sulfided these catalysts in hydrogen sulfide stream, 15% in hydrogen. So the pre-sulfiding condition was 400 degrees C for 2 hours in hydrogen sulfide stream. And for the TPR and TPS experiments that I'm going to describe the results of in the later part of this talk, we detected hydrogen and hydrogen sulfide with either TCD or photochromass spectrum. This is one of the mechanic results that we got with normal heptane conversion versus the fluorine content. As you see here, in this normal heptane conversion, we have both isomerization. We have both isomerization and hydrocracking of normal heptane. So this conversion includes both of these reactions. As we add fluorine, the activity increases and goes through a maximum when the fluorine content is about 2.5%.
goes down after more fluorine is added beyond 2.53%. Have the next one, please. We see a similar trend when we test these catalysts for hydrodesulfurization of diaphragm. Again, it goes to a maximum, showing the maximum at 2.58% of fluorine. And the trend does not change. Can you focus this a little bit? Could you focus it? Does not change, although we change the temperature for sulfiding between 300 to 700 degrees C. So regardless of the sulfiding temperature, we see the same trend of maximum activity as the fluorine content of 2.58%. Now, the question is, this kind of result is not unique with our work. Actually, many researchers have reported similar results that they observed the maximum activity on the cobalt molybdenum sulfide catalyst or nickel molybdenum sulfide catalyst. This may be the first one showing this the trend for nickel tungsten, but that's not very special. This kind of phenomenon has been observed by many people on the similar catalyst. Now the question is why? Why does that show the maximum at certain amount of chlorine content? So what we have done was to try to characterize the catalyst surface using different characterization methods. The first one is TPR. Next one. Oh, sorry. This is infrared. I'm sorry. Yeah. The first one is infrared. We observe the infrared spectrum of pyridine adsorbed on the catalyst, so that we may identify the kinds and the amount of acidic sites. Gamma alumina carries mostly Lewis-type acid sites. So as you see here, without any fluorine added, we basically have this 1540, this peak near 1540 wave number is said to correspond to the Brastes-type acidic sites, whereas these peaks all represent the Lewis-type acid sites. So as you see here, without any fluorine added to the catalyst, we basically see mostly the Lewis-type acidic sites. But when we add fluorine to the catalyst, we start to have this Brasted-type acidic sites showing up. So we try to measure the amount of acidic sites, just assuming that the extinction coefficient for this peak and this peak, we took this peak as a representing the Lewis-type acidic sites. Just assuming that the extinction coefficient for these two peaks are the same, we try to estimate the amount of acidic sites, and the results are shown in this table. As you see here, the Brasted sites increases with fluorine addition, and also the Lewis sites also increases. But one thing interesting here is that the amount of Brasted site goes through a maximum when the fluorine is 2.5. It's 9.7 here, and it goes down to 8.15 when we add 4% fluorine. So this is in agreement with our kinetic results if we try to correlate the amount of acidic sites, the Brasted sites, with the activity. And the total amount of acidic sites, in other words, the Brasted and Lewis acid sites altogether also go through maximum when the fluorine content is 2.5%. So it looks like that there seems to be some correlation between the kinetic results and the amount of acidic sites. Can I have the next one, please? And the next one is the TPR result. We did TPR on nickel only catalyst, and this is for nickel catalyst, and this is for tungsten catalyst. And the next one I will show nickel tungsten catalyst. Initially, I'll talk about this nickel one first. The TPR peak on nickel catalyst without any fluorine looks very simple. So we basically have just one major peak. But as we add more fluorine on the catalyst, the peak becomes very complicated. So that means that we have many different aspects of nickel particles supported in alumina when we have more fluorine. So it becomes complicated, and also the area of the peaks seem to become bigger. Now for the tungsten shows a peak near 675 or around 600 degrees centigrade, and it also becomes bigger with more fluorine. And also and an interesting thing is that the peak position seems to move to a lower temperature. So it looks like that we can reduce tungsten relatively easily when we have more fluorine catalyst. Can I have the next one, please? The results on, could you focus, please? The results on nickel tungsten catalysts are these. And I think the first peak here is from nickel, because that's the position that the nickel catalyst show the TPR peak. And these two, this high temperature peak seems to be from tungsten. And as you see here, we start to have a new peak appearing when we put fluorine on this nickel tungsten catalyst. It may be from tungsten or from a new phase, which is a combination of nickel and tungsten. Anyway, there is a new peak showing up at higher content of fluorine. Right? Okay. And also, I would like to draw your attention to the fact that the position of this peak, which is 610, is lower than the position of this peak, which is 630 degrees C. So maybe because this peak has been merged with this peak, but anyway, it looks like that this peak shows a little bit lower temperature than this one, which this is the catalyst that showed the highest activity in our kinetic results. Can I have the next one, please? The next experiment was temperature program sulfidation. Again, this is for nickel and this is for tungsten. Without any fluorine, we have a sulfidation of nickel catalysts from very low temperature to very high temperature. So we have very continuous sulfidation process throughout the whole temperature ranges. But when we add fluorine, we start to see a very relatively sharp peak appearing and becoming intenser, as you see here. So it looks like that the sulfidation of nickel is occurring at a relatively low temperature at one time, compared to this non-fluorine nickel catalyst. And here, for tungsten catalysts, the shape of the peaks look similar. The position of the peaks move to lower temperature, similar to the case of temperature program reduction. So it looks like we can sulfide tungsten catalyst at lower temperature when we have fluorine in the catalyst. So these results lead me to believe that the nickel, especially the nickel catalysts, seem to be dispersed more in more small particles. If the nickel particles are big, it may take a while to sulfide the nickel oxide particles into sulfide, because this sulfur has to exchange with oxygen. If the particles are big, it should be a slow process, whereas if the nickel particles are small, then it does not take a long time. You can just exchange it very rapidly, and sulfur does not have to go into the inside of the particle very long. Okay, similar phenomena, similar thing may happen for this tungsten. Anyway, the next slide shows this nickel tungsten catalyst. Here, this is the position that showed the peak for nickel catalyst, and tungsten peaks showed here, around here. Here again, we see that a new peak is appearing between about 225 to 450, which is around about 400 and 300, which was not observed in case of nickel or tungsten only. And this peak seems to become sharper and seems to appear at slightly lower temperature. I should have drawn a vertical line here to show that this peak indeed shifts to lower temperature when we have fluorine. So, summarizing the results of TPR and TPS, I can say that it looks like that either nickel or tungsten, those supported particles seem to be dispersed in smaller particles when we have more fluorine. And also the temperature reduction or sulfidation seems to be lowered when we have more fluorine. Those two, I can conclude. And the next one is diffuse reflectance spectroscopy. This is for nickel. We could not observe any significant spectra for tungsten. So this is the nickel. And when we treat nickel catalyst supported on alumina at low temperatures, at relatively low temperatures, below 450 degrees C, the nickel ions migrate, diffuse into alumina and form either bulk or surface nickel aluminate phases. And it is said that these nickel ions are coordinated either octahedrally or tetrahedrally. And this peak occurring between 350 and 450 are assigned to octahedral nickels, whereas these peaks are assigned to tetrahedral nickel. So we see that this octahedral nickel peaks are showing, whereas the tetrahedral nickel are very few. Right? Can I have the next one? For the nickel tungsten catalysts, we also see this peak, which may correspond to the octahedral nickel one, but the position of this peak is a little bit higher than in the case of nickel. In case of nickel, the octahedral nickel ions show around 350 and 400, whereas in this case the peaks show near 450. So even though it is related with nickel, it may not be just pure nickel itself, but it may have been combined with tungsten, so that it forms a nickel tungsten oxide phase. And an interesting thing here again is that the peak is the largest when fluorine is about 2.5 weight %. Okay, so this new phase appearing, well, in case of nickel tungsten oxide, in case of nickel tungsten catalyst, may be related with the active sites of the sulfide nickel tungsten catalyst. And the last, we observed the NO infrared spectrum of NO adsorbed on this catalyst. NO is said to, these are for the sulfide catalyst. NO is said to adsorb selectively on the edge side of this nickel or cobalt molybdenum sulfide catalyst. So we expected to observe the edge sides of this nickel tungsten catalyst by observing this infrared spectrum of NO. But in case of nickel catalysts, we do not see any major change in the spectrum of NO as a function of fluorine. They look basically the same. And the peak locations are also almost same. So are the tungsten peaks. They do not show major difference as a function of fluorine addition. But in case of nickel tungsten catalyst, can I have the next one? They, as a whole, they may look very similar. They have a very complicated structure. So as a whole, we cannot tell anything just by looking at the whole spectrum. But we try to deconvolve. We did the convolution process to separate this spectrum into divides this spectrum into three major peaks. We intentionally added this peak because this was the one observed for the case of nickel. And we assigned these two peaks for tungsten. And after this deconvolution, we observed that this number 2 peak is the largest, which we assign to either tungsten or nickel tungsten phase. It is the largest, and this is the catalyst with the 2.5 weight percent catalyst, 2.5 weight percent fluorine. So, to summarize the results of this FTIR and the DRS, it looks like that we have a new phase of nickel tungsten oxide or sulfide phase, which grows the biggest when we have about 2.5 weight percent of fluorine, right? And this may be related with the activity results, the kinetic results. Let me summarize my talk in the last slide. Okay, this is not a good summary, but well, I will just summarize my talk briefly. The effect of fluorine addition on nickel tungsten sulfide catalysts may be summarized into 3 points. One is the increase in the acidity, the Bronsted and Lewis acidity, which may be obvious, right? And we have an increased activity of hydrocracking due to this acidity increase. Anyway, acidity increase is one thing, and the other one is higher dispersion of particles and also easier reduction of sulfidation. That's the second point. And the third one may be appearance of a new phase, maybe nickel tungsten oxide or sulfide phases, and that enhancement of this phase at higher fluorine content. That's the observation that I have found. I know that I still need further study to clarify what the real nature of this nickel tungsten oxide phase is, and why this 2.8% is optimum to produce the maximum activity and so on. But this work is still going on, and maybe I'll talk more in the next occasion. Thank you. Thank you for your attention.
Excuse me, we have time for 1 or 2 questions.
I don't think you indicated what happens to the structure of, say, the alumina or any of the species that you put on the alumina after adding the fluorine. For example, could you do X-ray diffraction or something that would allow you to determine structural properties?
We did the XRD study, but we did not quite find out any distinct change. Particularly for the case of 2.8%. We tried to find out any major changes in the structure of alumina, especially for the case of 2.58% fluorine, but we could not find.
Okay, the surface area of the alumina was unaffected by addition.
Not very much. Not very much.
It is well known that during the high temperature hydrotreating, the fluorine compound may be dissolved, removed from the catalyst surface. So what you can say about all your effects, I mean, increase of activity during time of stream.
You mean talking about deactivation, changing the activity during the reaction?
Yeah, during the reaction.
I know that fluorine
during time of
is,
stream.
but it goes through a certain deactivation, but not very rapidly. So in the course of a reaction, it did not go through a very rapid deactivation. If we run it for a long period, it may change. In the actual commercial process, they keep adding this fluorine compound to the stream. In our case, we did not keep adding it. We just treated alumina with fluorine and then tested it for reaction. But in our reaction tests, it did not change very much.
Thank you.
I know that fluorine is being removed during the long period.
Well, you're trying to correlate with the acid sites because the addition of the fluoride may increase the acid side. But I think I missed that point. In your data, is that you have that data for at the several temperatures and the conversion versus the sulfur content, fluorine content? I'm sorry. Is that the tracking activity or the hydrodesulfurization activity?
Both.
Both of
One
them?
case was for hydrodesulfurization and the other one was for normal heptane conversion. The conversion includes isomerization and hydrocracking.
Okay, the reason why I'm asking is that usually, as far as I know, hydrodesulfurization is not dependent on the acidic sites on the surface. Hydrodenitrization is a little bit some relation with the acidic point, but not
Well,
HDS. But you're trying to correlate with the HDS
Well,
with the.
I think I should say that I'm not trying to correlate the kinetic results only with the acidity itself. But I believe that the acidity and dispersion and easy reduction and the appearance of this new phase, they all work together to make this maximum activity that I observe. That's what I'm trying to say. It's not the only one factor that contributes to it.
Let's thank our speaker for a good Our next talk will be on the comparison of carbon and alumina as supports for cobalt molybdenum catalyst in hydrodesulfurization. Speaker will be Professor Song-Ki Im. Professor Im received his bachelor's science degree in chemical engineering from SNU in 1969. His master's, and then he spent about 4 years working for the Korean fertilizer company. Then he went back to school, received a MS and his PhD degree in chemical engineering from SUNY University in Buffalo. In 1978, he joined the faculty of KIST and has been active in the KICHE. He's now the executive director and editor of the Journal of the KICHE. He's Secretary General of the Catalysis Division.
Thank you, Mr. Chairman. Among his introduction about myself, some parts is just misleading. I have been former. I served as former staff of KICHE, and I was former Secretary General of Catalysis Division, not now. Today, I don't have to express how I feel as a speaker, especially Korean speaker, because Professor Moon has already described the things already. And concerning the activation of English speaking, I think I am a better example. And I would like to go one step further. So this is a very nice afternoon time.